ordering of these terms. Okay, so what are the terms we have obtained? We have obtained, so for the process, what we are trying to look at. So everybody is following what I am doing. So we are considering a process, so in which this is happening. So you are having this B goes as electron positron, clear? A boson decays into two particles, and we are trying to figure out the S matrix, clear? So we are trying to figure out actually the S matrix elements. So at the third order perturbation, we have seen yesterday this kind of term, and we have already obtained one diagram. So let me write those terms again, so that you will understand it properly. So we have to put all the possible contractions. So this is one of the contractions which we have already seen. This psi bar is contracted with this psi, and this psi is contracted with this psi bar, and we have contracted this phi and phi. Okay? So this is one of the terms, and another term, and all the possible contraction, three fields we are left with: phi, psi bar, and psi, which represents our process. Clear? Okay, so let me take the another contraction. So you are having psi bar psi phi like this thing. Okay. Then you are having psi bar psi phi. Okay, so what is the another contraction? We contracted, let's say, this psi and psi bar, and then we contracted this psi bar and psi, and we contracted this phi and phi. Okay, so plus other, I will show only this very term, plus other contributions. Now let's look at the diagram, what we can obtain from here. So I have already told you how to obtain the diagram. Clear? Okay, so now let's try to obtain the diagram from here. Okay, so let's go. So now let's look. So you are having forget about the contractions for the time being. Clear? So let's forget about the contract. What is remaining? You are having phi. Clear? So you are having this phi here. Then you are having psi bar here, and you are having psi here. Clear? So it means you will be having the annihilation of the boson, because the process requires the annihilation of the boson at some space-time point. So it means you are having annihilation of the boson at which point? At x1. Clear? So let's write that. So you are having point x1, let's assume. So you are annihilating the boson. Clear? Got it? Now what is the another term? So another at point x3 you are having psi bar and psi. Clear? So that means at point x3 you are creating what? What you are creating? You are creating an electron positron pairs. So let's call that x3 this very point. So you have created an electron positron pair this way. So this is your electron and this is your positron. Clear? So now we have to connect the dots. Huh? So this is your point x3. Okay, so now how to connect the dots? Now let's first look at this x2 and x3. There is a contraction between x2 and x3. Phi field is contracted. Clear? So it means I have to put one more point. Let's write a point here which describes our point x2. And from x2 and x3 there is a contraction. So the internal line. Clear? So now let's look at from x1. So you are having psi bar and psi. Two contractions between what? x1 and x2. Clear? Two fermion fields. Okay, you are having one pair psi bar and psi, and then you are having psi and psi bar. Both get contracted between which points? x1 and x2. So that is you are having, since the contraction of fermion fields gives you the fermion propagator, clear? And the contraction of the boson fields yields you the boson propagator, clear? So we have written a boson propagator here, and now I will have the contraction between x1 and x2. Let's write it line like this thing to differentiate between the two things. It's a kind of loop. समझ आओ? So you can write it like this way. Okay. So now this is your typical. How many vertices are there? 3 vertices are there. Okay. So this is one vertex, another vertex, and another vertex. Clear? So now this diagram contains how many propagators? 3 propagators. Okay. And these appear as the internal lines of the diagram. And the process requires actually 3 external lines corresponding to 3 external particles. The initial state particle, that is the dotted line from the left, and the final state, those are the bold lines on the right. Clear? Samajh? Okay, so this contains one loop. Yesterday we have already seen one loop diagram. Clear? Samajh? Okay, so let's take another contraction, what you can think. Okay, so let's take another contraction. Any question? So let's take any arbitrary contraction. Okay, so you can think that, let's say you want to contract at the point x1, both the fields at x1, like this thing. So you are having this psi bar psi phi at x1. So I will take all the possible contractions. So those you have to figure out. So I will go only up plus all other contractions. Those you have to figure out. I will take one contraction here. Let me contract these two fields. Let's contract these two fields. Because I have to contract a psi with psi bar. Okay? So this is also the possibility. Is this a possibility? Okay. So this is also a possibility. Now I have to contract the phi fields. Okay? So let's contract these two fields. Okay? So that means at points x1 and x2 all the fields are contracted, but the points of the fields at x3 they are not contracted. Clear? Okay, so let's draw the diagram. So I will take a point x3 for example. So phi you require for the annihilation of the boson in the initial state. So it's like this. Then you are creating electron positron here. Clear? Okay, so now let's look at these contractions where they are. So it means you are having x1 and x2. So let me take any x1 here and x2 here. So this line is not connected with, there is no connection between x3 and x2 or x1. Clear? They are all independent. This is not connected. So let's call this as x2, call this as x1. So you are having contraction of the fields where at point x1. Clear? So that means the field gets contracted with itself. So it's something I should say like this. Okay? Because it comes back to the point. So similarly you are having here. So kind of thing. Okay, so what is then there is a contraction between x1 and x2. Okay, so you see this is actually a disconnected diagram. So this part is not connected with the, and they do not actually contribute to the calculations. When we calculate, let's say, scattering cross section or the decay rate or any damn thing, any physical observable what we try to calculate, these disconnected diagrams does not connect. This is a connected diagram. All the parts of the diagram are connected, is it? But here all the parts are not connected. Samajh aaya? Or you can equally think, let's say, instead of this contraction, you can think this way. Okay? So you can think, let's say, you want to take this psi bar is contracted with this psi, and this psi is contracted with psi bar. Let's say, take the contraction between two fields at x1 and x2. Forget about x3. Clear? So, this will yield me this kind of diagram. Okay, so let's try. So you are having at x1 Okay, let's write this as x2, this as x1. Okay, so you are having a phi field that's contracted. Clear? Phi and phi is contracted, and what you are having, psi bar and psi. It's kind of this thing. Okay, one psi bar will give you this bold line, solid line. Another psi bar psi will give you the another bold line. Clear? And phi phi contraction will give you the dotted line. This also what? Disconnected. Huh? Got it? So you think when you do all the possible contractions, you will be getting only few diagrams which are connected. Most of the diagrams you will get what? Disconnected. Okay, we will discard the disconnected diagrams. समझ आओ? Any problem? Huh? Okay. Have you written this? Okay, so now let's take. Okay, since we are dealing with, let's say, a decay of a particle into two pair of particles, clear? Into a pair of particles. So that means initially I start with a particle which is actually a free particle unless it there is a sort of interaction and it decays, clear? And you receive those particles as a free particles. So if you start with the free particle states and end up with the free particle states again, and you know the free particles are always represented by the plane waves, and the plane waves are not normalized. So we need to figure out a procedure to normalize those plane waves. And in quantum mechanics, you know, we do it through the box normalization. So we restrict our plane waves in a box and do the normalization, and then let box go to the infinity. I mean, let the dimensions of the box go to infinity so that it represents perfectly your plane wave. So this is an idea what we are trying to do. You will see its utilization in a moment. So let's take the concept of the normalized states. Okay? So let's define. Let 0, okay, this cat 0 be the vacuum state of the vacuum state. Okay? So what does that mean? It means if I apply the annihilation operator on this vacuum, so it gives me the 0. And we assume this vacuum is normalized. Clear? So I am assuming the vacuum to be normal, and it's a physical thing to assume it to be normalized. Okay? Now tell me, what are the dimensions on the right hand side of this formula? You are having an identity, it is a dimensionless, clear? So that means the dimensions on the left hand side should be also, it should be a dimensionless quantity. So in other words, I can choose this vacuum to be dimensionless quantity. So it's a, so we take it to be dimensionless. Since we are working in h cross equal to 1 and c equal to 1 units, that means natural units. So we will be describing all the units in terms of the mass dimensions. Okay? So let me repeat it again. What we mean by that. So let me give the idea of the mass dimension or the energy dimension sometimes. Okay? Mass dimension or energy dimension, they are one and the same things. Okay, so you put h cross equal to 1 and c equal to 1. Clear? So what your formula becomes? So this E equal to mc square, it becomes simply. Clear? So that means the mass is having the same dimensions as energy if you put C equal to 1. Clear? So we write the dimension formula for this E or the dimensional formula of F as 1. So the mass dimension of this energy is 1 in terms of, so it is m raised for 1. Clear? Got it? Now let's look at the momentum. So what is the mass dimension of the momentum? So moment, okay, can anyone tell me? So what is the relation between energy and momentum? E is equal to p square by 2m, simple, okay? So you need to calculate what? Energy, okay, dimension of the momentum. So what does that gives me? So momentum is same as the energy, because in the denominator you are having mass. Okay. So one mass will cancel with or mass into energy. Like this thing. So you are having P square equal to twice m. Clear? So what it means? Twice me. So the here it is what you are having 1m multiplied by another m. It means the mass dimension of P is 1. So that means P will scale as the energy or P will scale as the mass. Invariant mass. It means it is an invariant mass quantity. You know? So mc square is an invariant quantity. You know? Okay? Everybody got it? Now you can calculate what is the mass dimension of the force. Okay, so what is the mass dimension of the length? So now let's look length in terms of now energy. Okay, so you'll know the de Broglie's hypothesis. So that gives you the relation between momentum and the length. Clear? So momentum is the mass dimension, or momentum scales as the energy. Okay, so it means length will scale inverse as the inverse of the energy. Clear? So in other words, the mass dimension of this is -1. Or in other words, length is okay. So this length is same as actually mass raised for -1. So, so similarly, what is the mass dimension of time? T. So you know the relation delta T delta E is equal to proportional H cross is equal to 1. So delta T or T will be inversely energy. So in other words, the mass dimension of time is also -1. So that means length and time will scale as m raised for -1, and momentum and energy will scale as mass raised for 1. Got it? So this is the idea of natural units. In field theory, it's very useful to to take the natural units and look everything in terms of the energies or in terms of the mass. So now let's take the example. Let's calculate the mass dimension of the momentum. Mass dimension of the field. This we have already done. Let me repeat it here. So we are having action. So let's take the action. That's equal to, let's say, d4 of x and Lagrangian. Clear? So this is how we write the action in 4-dimensional space-time. Okay? This is actually Lagrangian density instead of the Lagrangian. I will take this as the Lagrangian. Okay, action is having the units of h cross. Okay, units of action is what? Units of h is equal to h cross. So that means since h cross is equal to 1, so this is dimensionless. So in our system, natural units, the dimension of s is equal to 0. So it is dimensionless. Clear? Okay. So if this is dimensionless, now let's calculate the dimension of this L. Okay? So what are the dimensions of this d4 of x? It is the length. Okay? So the dimensions here, they are simply m raised power -4. It is actually 4 times length. Length multiplied by length. Okay, rather length into time. Clear? So length and time goes as m raised for -1, so it will be m raised for -4. Let's take the mass dimension of this as n or x. So it has to be equal to mass raised for 0. Clear? So what it gives me? D has to be equal to 4 in 4-dimensional space-time. So in other words, the mass dimension of this Lagrangian must be what? 4. Clear? So if it's a d-dimensional object, what should be mass dimension? It should be d. Clear? Yes, sir. Okay. Now let's look at, so this is from the Lagrangian. Now I know in 4-dimensional space-time, Lagrangian always has the mass dimension of how much? 4. It goes as actually the m raised for 4 term, such that this action remains invariant. Okay, so now let's take the scalar field. So you are having scalar field, this L is equal to 1 by 2 partial mu phi minus half of m square phi square. Now principle of homogeneity says the dimension, if you write a quantity, the dimension of each term must be same, is it? So that means dimension on left hand side should be the dimension on the right hand side. and the dimension of each term on the right hand side should be same. So let me pick up this very term because this is very simple to do. Okay? Clear? So now what is the dimension of L? So dimension of L is equal to 4. So now I have therefore dimension of this mass square m square phi square. So it should be what? 4. So now what it's, let's assume this m is the mass of the particle. Okay, let's assume it is the mass of the particle. So this gives me m square. Then phi should be having the dimension of what? 1. Because it will be what? M square multiplied by m square. Okay, so which gives me what? Dimension of phi should be 1 in 4-dimensional space time. Clear? Mass dimension of phi should be what? 1. Now let's take the Dirac field. Everybody followed? So this is m square. So it will be m raised to 2x. X means the dimension of what? Phi. So solve the equation 2 plus 2x is equal to 4. So you will get x is equal to 1. Got it? Okay. So now let's take then a Dirac field. So let me take the Dirac field. So your having L is equal to psi bar like this thing minus m psi bar psi. I mean partial slash. It is gamma mu. Take the last term. Okay. So the dimension here is what? So it is m. So let's say this is m raised for x and this is m raised for x. Clear? So it should be what equal to? M raised for 4. So you are having 2x plus 1 is equal to 4. So what is x? 3 by 2. So that means mass dimension of Dirac field psi is how much? 3 by 2 in 4-dimensional space time. So that means in 4-dimensional space time the scalar field varies as the energy and the Dirac field varies as energy raised for 3 by 2. So in other words I can say like this thing. Okay, so this phi varies as some energy and psi varies as what? Energy raised for 3 by 2. Okay, so when we do, actually this is very important thing in when we do, I mean renormalization or regularization, there you need to understand actually the dimensionality of the let's say a given quantity what you are trying to calculate. Okay, based on that notions you will be able to understand whether the quantity you are calculating is divergent, okay, towards the longer momentum or divergent towards the low momentum. So this helps us to understand actually the behavior of the fields at any energies. Clear? Okay. So now let's go to I mean these normalizer states. Okay. So let's say I have defined this A of P. Okay. So I have defined vacuum like this thing such that vacuum is what? And I am taking this vacuum to be dimensionless. So that means it does not have mass dimension. Clear? Okay. So now let's create a one particle state, single particle state on this vacuum. So that means I have to apply a creation operator on the vacuum. Clear? So let me write a single particle state. Okay. So let's calculate the single particle state. So it means A dagger of P acting on this vacuum, it should give me a single particle state. So it means a particle carrying a momentum P. P is the 4 momentum here. Clear? Now let's check the okay. So I have started with vacuum which does not have a dimension. Now let me check what is the dimension of this thing. Okay. So physically you should okay. You can say if I am having if you are creating a quantity from a dimensionless quantity, it should be also what? Dimensionless. But it's not true here. So let's check the dimension. That means that if I know the dimensionality of this very state, it gives me the dimensionality of this cat state P. Clear? Okay, so let's check it. So what I need to figure, I also know this is dimensionless quantity, and I need to check what is the dimensionality of this A or A dagger. Clear? So let's check it. So from phi field this, okay, so you are having phi of x like Is it like this? 2 by q. Yes, 2 by q. Then ARP e raised to minus r p dot x a dagger p e raised to r. So this is the Fourier expansion of this phi field. Now what is the dimensionality here? Okay, so I am having dimensionality here is 1. Clear? So I need to check the dimensionality of this A or P, or that will give me the A dagger P. Clear? This object is dimensionless because it is an exponential. So समझ आओ? It's P dot x, it is exponential, it is dimensionless. Clear? Clear? Okay. So now let's check the dimensions of this thing. So how many P's are involved here? 3 P's. It is D3P, that means 3 P's. Px, Py, Pz. So what is the dimensionality here then? Mq. Clear? So you are having energy here. What is the dimensionality of the energy? M. Clear? So what is the dimensionality of this very object? It is Mq M. So it is M raised for half minus 1 by 2. So that is M raised for 5 by 2. Clear? So how much you require? On left hand side, how much you require? 1. So that will fix the dimension of this A. Clear? So it means A dimension of this A must be equal to minus 3 by 2. Now if I multiply this thing, so you are having 5 by 2 minus 3 by 2. How much is that? 1. So that means now the dimension on this side is also what? 1. Clear? Got it? So this is very trivial exercise. Okay. Now you are having the dimensions of A is 3 minus 3 by 2. It means the dimension of what? A dagger is also minus 3 by 2. Or okay. So now let's look here. So what are the dimensions therefore? So on this side, so the dimension of this object is what? Minus 3 by 2. So it means the dimensions of this state cat, so that's equal to minus 3 by 2. So you are having a dimensional quantity. Clear? To avoid this thing, okay. So I need to fix it up. I need to make it dimensionless. Got it? For that matter, okay. For that matter, what I will do, I will use the concept of the box normalization. Samajh? So since this is a plane wave state, it stretched from minus infinity to plus infinity. Clear? So what I will do, I will restrict it to a box and normalize it within a box. So samajh? And make it in that way. Let's make it a dimensionless quantity. Clear? Everybody got it? Okay. So now let me define the single particle states. Okay. So let's define this way. So I will define now this. Your time. Okay. So let me define my single particle state. So P. Okay. Let's take the bosonic case. So I will define it. Let's say this way: root of 2 pi q divided by some volume and A dagger of P acting on. Okay, V is the volume of the box. Clear? समझ आओ? Or you can write. Okay, so let me write. This is a single particle state. This P also means like this. A boson carrying the momentum. So let me write this way. Okay. So I will put the 3 momentum vector carrying the 3 momentum. Okay. Now let's look at what are the dimensions again. So this A dagger carries minus 3 by 2. What are the dimensions of this V? V is the length. So V is the length. It means M raised power minus 3. Clear? There is a root, that means M raised power, so it will go up. So it is M raised power plus 3 by 2, M raised power minus 3 by 2. So it's a dimensionless quantity. Clear? So now this is our dimensionless. Now you can create in this way any number of particle states. You can create 2 particle states, so on. Got it? And you will be having what? No dimensions at all. Clear? Dimensionless quantity. So this is the way you are creating actually, the particle states which does not carry any dimension. Okay, so what I have done here, I have kept it within a box. Samajh? Okay. Similarly, we can define for the electrons and for these positrons. Okay, for we define now this E minus P. S is the spin of the particle. Okay, so like this one. So F dagger is the creation operator for the particle. And now let me write E plus F tilde dagger, we write as okay. So this gives me the particle state. This is the antiparticle state. Clear? Now let's check the normalization. Huh? Let's check whether they are normalized or not. Okay. Since these are the plane waves, usually plane waves are not normalizable. Okay. So now let's look at whether they are normalized or not. Okay. So everybody followed it? Any question? Okay, so let me go to the next page. So let's write the normalization. So I am having now this B of P prime and B of P. So that means normalization of these scalar particles. Okay, so let's try to check it. So what it gives, so you are having root of 2 pi q by v in front, so you then 2 pi q coming divided by v, so it is 0. So you are having this a, it will be simply a of p, clear, and here it will be a dagger of, so it's p prime, so it's p. Okay, so I just used the previous definition of this B of P and okay in terms of A dagger. When you write actually this brass state of this B of P prime, it will be like this thing. It is actually the conjugate of this thing. Huh? Okay, so what you get? So it's 2 pi q by V, so it is 0. So now let's use the commutation here. Huh? Okay, I want to put it in the form of, let's put A dagger first and then A, clear? So I have to use the commutation between A and A dagger. So what is the commutation relation? So you know A of P, okay, and A dagger of P prime. So what is the commutation? So that's equal to delta P, P minus P prime, clear? Samajh aaya? So now let's write this thing. So it will be something now, okay, A dagger of P, then A of P prime. The reason being why we need to put it in this form, because this annihilation operator annihilates the vacuum, so that this term will give you 0. Clear? So much, it's very simple to do this way. I mean, analysis becomes very simple. So then you are having plus. So A dagger will be given A dagger A plus this delta 3 P minus. Okay. So now this A annihilates the vacuum, it's equal to 0. Samajh aaya? And what remains there? So you are having 2 pi q by V, so it is simply delta 3 because vacuum is normalized. So this is the, the orthonormality condition. Now let's take P equal to P prime. Okay, so I have to figure out the norm of the state, clear? So if I take now P equal to P prime, so you are having this B of P, okay, B of P. So what you get? So it is actually an infinite quantity. Delta 3, 0. So it is in the momentum state, momentum space. Eh? So what is this delta 3, 0? It's a divergent quantity. It's a infinite quantity. Clear? So that means you are not able to figure out the norm of this very state. This states what we have defined. The reason being these are actually free particle states, and it is true for any kind of theory whatsoever, whether classical or quantum, so free particle, I mean the plane waves are non-normalizable. You cannot normalize what? Plane waves. Okay? What to do? Okay, I mean how to get rid of this, this delta 3p0, so that we have already done. We have to do the box normalization. I will confine my particle to a box. Okay? In that box, I will redefine my delta function and figure out what this delta 30 is. Samashyam? Okay? So what I will do, okay, so let's look at the delta function. Okay, so my delta function is usually like this thing. Let me write delta 3p. So it is something integration or volume, okay, d3x e raised power minus I. It's actually I think 2 pi dot x. Clear? Okay, over some volume. Let's say over some volume V. Is this, sorry, it is over the entire space, not the volume. Clear? So this is from minus infinity to plus infinity. This is how we define the delta function. Now what I will do, I will restrict my integral to the finite space. So let's write it this way. Let's write it. So I will write like this, in limit of v tends to infinity. Okay? Can anyone tell me what to do? So 1 by 2 pi q integral d3 of x, but over some volume v. Clear? Now I have defined my integral over a finite volume. Okay, e raised power minus I p dot x. Samajhama, at the end of calculation, what I will do? I will first evaluate this very quantity, but at the end of calculation, I will take v tends to infinity. Is it the same thing? Okay, this is the procedure of the box normalization. You put it within a box, figure out what is the value of your given quantity, and then make the dimension of the box going to infinity. Clear? Okay. So now, if I can write this thing delta 3 of 0, so let's write this. I mean p, I'm space time. We are in the momentum space here. Clear? So let's put this p equal to 0. What happens? So its limit of p tends to infinity. So it's 1 by 2 pi q. Okay. So it will be simply integration d3 of x. So what this object is? It's simply volume. Huh? Is this the volume? So it gives me the volume. So it is something limit of v tends to infinity, volume divided by 2 pi. Samajhama? So what I will do, I will use instead, okay, in the box, okay, in a given box I can use this delta 3 as what? V by 2 pi q. But at the end of the calculation, what I will do? Put v tends to infinity. So therefore, in a box of volume V, we write this delta 3 0 as 2. Okay? Samajhama? So now let's go to the previous thing. Any question here? Okay, have you written it? Have you written it? Yes, sir. Okay. So now let's go to the previous thing. So what you are having here? Delta 3p0. So what I will write? So now, okay. So I will write therefore, I will write this b of p, okay, and b of p. So what it is? So it was something. 2 pi q by v delta 3p0. So that's equal to 2 pi q b. Okay, so this is b divided by 2 pi q. Now what you got? It's equal to 1. Now it's normalizing. Okay? So you have now the normalization state. Clear? Okay? So in other words, what I will do, okay. Okay, any question? So Shama, similarly you can check now. Okay. So what we have arrived at, okay. So we, okay, similarly you can calculate this thing. I mean electron. So let's calculate this thing. Electron in the momentum state like this thing, S prime, then you are E, P, S. Okay, so let's calculate this norm. Okay, so let's calculate this norm. So it will be same thing as 2 pi Q by V. Okay, then you are having 0. So for an electron, what you need? So this E we have just written as, so as a 0. So there is an F dagger S P. Clear? So and here it will be F S prime. Okay. Yes, no? Is it? You sure? So F dagger creates, just we have just shown, F dagger creates you the particle state, and when you take its conjugate, it will be this thing. So this object is the conjugate of this. Okay, now we know the fermions. Okay, so fermions, I mean, do the anti-commutation. Clear? So what is the anti-commutation? So you are having F S prime P prime, and then you are having F dagger S P. So this anti-commutation is equal to delta S S prime delta 3 P minus P prime. Clear? So now let's use. You need to take this F dagger on this very side using this very anti-commutation. So what you'll get? Okay. So everybody has written it? Huh? Okay. So I can write therefore this equal to, so you are having this 2 pi Q divided by V. So you are having 0, so it will be something F dagger S P, rather with a minus sign. Okay, F S prime P prime. Okay, then you are having this delta S S prime delta P minus P prime. Okay, and it is 0. So what this gives me, F will act on the vacuum, it annihilates it. So it is 0. So you are having this as delta S S prime and delta 3 P minus P prime. Now you can write, let's say if for P equal to P prime, so this will become delta 0, correct? So for delta 0 you will write V by 2 pi cube, that will cancel with this thing. Okay, so this is something electron P prime S prime, electron P S, okay? Which implies therefore you are having E S, okay? So S E P S, the same thing. So it will be something 2 by Q by V. Delta SS is 1. So it will be simply delta 3 P 0. So that is 2 pi Q. The box normalization. So it's equal to V by 2 pi Q. So that's equal to 1. Similarly, you can do now. Okay. You are having this positron. Okay. So it's these states you can write as same thing, 2 pi Q by V delta SS prime delta 3 P minus. They will have the same kind of relation because positrons and electrons are fermions. They follow satisfy the same kind of relation. Clear? So you will be having this kind of relation, and you put P prime equal to P, S prime equal to S. That will be equal to 1 in the box. Clear? Samajh aaya? Any problem? Okay, good. So now let's calculate the single particle state, because now I need to calculate the particle state, how it looks in terms of the plane wave in this very box. Samajh aaya? Okay, then we will do the calculations. First you need to, okay, I have created a state vector, but I will take a look at how this state vector looks like as a plane wave. You will see it is actually the sum of the plane waves. Okay, so let's look at these things. So I know this phi plus, okay, phi plus actually annihilates the state, is it? Because we need actually a, we have this kind of operation. Okay, so we have this thing psi bar minus psi minus phi plus. Is it? In all the processes, whether you are having at the first order, third order, or any order, you need actually these three operators. Clear? So this acts on your boson state. Let's say it carries the momentum k, and it acts here what? This electron positron. Clear? So ultimately we need to calculate this very matrix element. Okay? So rest of the factors, let's say in the first order case there were no factors, there were no internal lines, and in the second order case, third order case, we are having internal lines, is it? So those are not operators, those are simply functions. Okay? So they will not come within this very, within this kind of, matrix element. Clear? So I need now to know how this phi plus acts on this bk, and how this psi minus and psi minus bar acts on these electron states. Clear? So I need to know the form. Okay? So let's write. Okay, so this phi plus of x acting on this b of k. So I will write now for the initial state momentum as k. Clear? So and I will write its energy as omega k, to distinguish between the energies of the final particles. Okay. So can anyone tell me how it looks like? So phi plus is actually d3k divided by root of 2 pi q twice omega k. It was actually ek, so I am writing here what? Omega. So omega is energy of the initial state. So you are having then this a of k, clear, e raised for minus I k dot x. Okay, it's acting on which state? So it is our phi plus. So clear? So now you are having b of k. B of k we have just written. So it is 2 pi q by volume. Okay, root. Then you are having what? A dagger of k. Okay, since k is already included here, I'll write it here as, okay, so let's write this as prime. So 3 prime. Okay, so acting on the right. So this is our b, is it? We have just defined this as b. Okay, and this is your phi plus. So let's work it out. Okay, so what this root of 2 pi q by v, this will come out. Okay, then you are having this integration d3k prime divided by root of 2 pi q twice omega k prime. Okay, then you are having this exponential e raised for minus I k prime dot x. Clear? Okay, then you are having this a of k prime, a dagger of k acting on this way. Okay, so so you can actually write a vector here, it doesn't matter, because everything we are doing at equal times. Okay, so now you are having this a dagger. What you will use? So this object is equal to, so using the commutation, it will be a dagger k. Then you are having a of k prime, then plus delta of delta 3 k minus 3. Clear? Everybody followed it? So just using the commutation. Now this A will annihilate the vacuum. Okay? So when this annihilates the vacuum, this will yield you what? So it means it's something like this term acting on the vacuum. So this yields me what? Is equal to 0. What remains there? Only the delta. Okay? So it is something root of 2 pi q by v. Okay? Integration over k prime root of 2 pi q twice omega k prime. Okay? E raised for minus I k prime dot x, and you are having a delta 3 k minus. So now you integrate over k prime will be replaced by what? K. So it will be simply equal to, so and here is a vacuum state. Okay, so vacuum will be there. Right? Okay, everybody got it? Okay, so what this will be equal to? So this is equal to So let me write it on the next slide. Everybody has written it? Huh? Okay. So I will erase it here. Okay, there is actually a subtlety here, because this is actually the 4 momentum vector here, but the integration is over only what? 3 momentum. So let me show you here. So what it is? It's like this thing. E raised power. Okay, so let me go to the next page. So it's something. You are having e raised power minus I k prime dot x. It's some like this thing. E raised power minus I omega k prime t minus. Okay. So what is it? Anybody? Because we are actually in the interaction picture. In the interaction picture, this time dependence is removed. So let's think over it. So what this will be? It will be simply when you take integration over this k prime will be replaced by k. So that's simply equal to root of 2 pi q divided by v, and there you are having 1 divided by root of 2 pi q, okay, twice omega k and e raised power minus I k divided by. So how does it matter? So h is the 4 vector itself, so it doesn't matter. So can you tell me why? Can you tell me why? Okay, so let me write. So it is e raised power minus I, okay, omega k prime t minus k prime dot, okay, x. Clear? With the help of delta function, k prime will be as same as what? K. So when k prime is same as k, so this k prime will be k. Clear? So it will be same thing then what? So e raised power minus I omega k t, okay, minus k dot x. So that is same as what? E raised power minus I. Let's write k dot x. So it will be e raised power minus I k dot x. Here it's a 4 vector. Clear? समझ आया? There is no problem. So now this 2 pi q will cancel out. What remains there? So therefore what we have, okay. So what we have, so I am stopping. Okay, so what we have, so then we are having this very state, phi plus of x, it acts at the point x, when it acts on this boson state, when it annihilates it, so it looks like this thing, 1 divided by root of, there is a v, is it? Yes. So it is something root of v twice omega k, clear? And then you are having e raised power minus I k dot x acting on the vacuum. Now look here, it's actually e raised power I k x gives me what? It's a plane wave, is it? So that means the single particle state is what? A plane wave. So this particle travels as a plane wave. समझ आओ? Similarly, can you do it for the other cases? I mean for the fermion and the antifermion? Huh? Or shall I stop here? Okay, so let's stop here. Okay, so wait a second. You can take the conjugate of this thing, which implies the conjugate of this thing is b of k, okay, acting on. So it will be phi minus, because it is an annihilation operator in this direction. When you take the conjugate, it will become a creation operator. Clear? Phi plus dagger is actually phi minus. Okay, so it is something. So this is very important factor, this root of v twice omega k. So समझ आओ? Okay, so let's stop here.